Hello, my listeners. My name is Mr. Kugonza. I'm going to present to you the last lesson on this topic of potentiometers. This last lesson is going to be about potentiometer calculations, part 2, implying that there was part 1 that we earlier on looked at. This is also the 5th lesson on this topic. Example 1. In the circuit on the next slide, X is a battery of negligible internal resistance. AB is a uniform wire of length 1 meter, diameter 3.57 times 10 power minus 4 meters, and resistivity 1 times 10 power minus 6 ohm meters. When switch S is thrown to position 1, the galvanometer shows no deflection when AD is 80 centimeters. When S is thrown to position 2, the galvanometer shows no deflection when AD is 40 centimeters. So this is the diagram relating to the question that I have just read. We have a cell X, we have a resistor of 998 ohms in the circuit, together with another resistor of 992 ohms connected in series with a potentiometer wire AB, whose resistance is 8 ohms. And then there is a thermocouple and another cell whose EMF is 1 volt. We have a two-way switch. Position 1 is the lower position, position 2 is the upper position, and a galvanometer, of course. So we would like to find the EMF of the thermocouple. That is the question. First, find the resistance of AB, the wire AB. That is what we are going to find first. Then the EMF of the thermocouple, and then we will also find the EMF of cell X, because the EMF of that cell is not given. So how do we get the resistance of wire AB? In order to get the resistance of that wire, we use that formula. The resistance is equal to resistivity times length over cross-sectional area, because all those quantities are given in the question. So the wire has a resistivity of 1 times 10 power minus 6. Length is 1 meter, so 1 times 10 power minus 6 times 1 divided by pi d squared over 4. That is now substituting the area of a wire. A wire is considered to be a cylinder, and therefore the cross-sectional area is pi d squared over 4, or pi r squared. So computing from a calculator, this value gives us 10 ohms. So we have calculated the resistance of wire AB. We can now get the current which flows through the potentiometer wire by looking at the first condition, when the balance length is 80 centimeters, and that happens when the switch is thrown to position 1. So in that case, there is an unknown current I that flows through the 992 ohm resistor and through the potentiometer wire up to the balance point. So the total resistance up to the balance point is going to be 10 out of 100, which is the resistance per centimeter of the wire, times 80. That alone gives us 8 ohms. 8 plus 992 gives us 1000 ohms, times I equal to 1, the EMF of the lower cell. So why do we equate 1 to the PD from the extreme end on the left hand side up to point D? It's because that PD balances with the EMF of the cell, the 1 volt cell. So that's why we say that current I is therefore going to be 1 out of 1000. Now going back to the wire, since we have got the current flowing through it, and we know the resistance of the wire is 10 ohms, not 8 as I earlier mentioned. It is 10 ohms. So 1 out of 1000 times 10 over 100 gives us 1 over 10,000 volts per centimeter. So we've got the value of K. And then the second balance position is the 40 centimeters when the thermocouple is connected. So therefore, the EMF of the thermocouple will be the PD per centimeter times 40. That gives us 0.004 volts, which can also be written as 4 millivolts. Okay, then the last question is determining the EMF of cell X. So since we know the current passing through produced by cell X, and we also know the total we can compute the total resistance of the primary circuit, 992 plus 10 plus 998, then which gives 2000 ohms. 2000 times 1 over 1000 gives us 2V. So we have got the EMF of the driver cell. Let's look at another example. In the figure on the next slide, X is a battery of EMF 2V and negligible internal resistance connected in series with a 2 ohm resistor and AB of length 1 meter and resistance 2 ohms. This is the diagram. This is the diagram relating to the question that I have just read. So would like to find the question says a dry cell Y of EMF 1.5V and internal resistance 1 ohm is connected in series with the two resistors R1 and R2. The galvanometer shows no deflection when connected respectively from points B and C to points on AB 50 centimeters and 75 centimeters respectively from end A of the wire. Find the current flowing through R1, 2 the resistance of R1 and R2. So what we need to do is to first of all calculate the current from the lower circuit. Since the EMF is 1.5 and the total resistance is R1 plus R2 plus 1, therefore the current is 1.5 over R1 plus R2 plus 1. Now the PD across R1 is IY times R1. That gives us PD across R1. Then we also get the driver current. Since the EMF of the driver cell is 2 and the total resistance in that primary circuit is going to be 8 ohms, the resistance of the wire plus 2 ohms which is in the circuit, giving us 2 out of 10. Since the resistance per centimeter is going to be 8 out of 100, so 8 out of 100 times 2 out of 10 gives 16 out of 1000, which becomes now the PD per centimeter. So 16 out of 1000 times 50, the first balance length, gives us 0.8 ohms, 0.8 volts. So equate 0.8 V to 1.5 R1 over R1 plus R2 plus 1, because this value was the PD across R1, and that was obtained when the balance length was 50. So that is our first equation. Now, when the galvanometer is transferred to position C, the PD is now between both resistors R1 and R2. So we need to calculate the value of V equal to IY into R1 plus R2. And that is going to be represented by this equation, 1.5 over R1 plus R2 plus 1, which is current, into R1 plus R2. Again, PD per centimeter is 16 over 1000 times 75. That gives us 1.2. So this 1.2 is equal to this other expression here. When you equate those two, we now have the second equation with two unknowns. So we have equation 1 and equation 2. We are able to get R1 and R2 to simplify. The best way to simplify that is to let R1 and R2 equal to X. First find the value of X. From equation 2, we have now turned equation 2 into 1.5x over x plus 1 equal to 1.2, get x equal to 4. And then equation 1 becomes this. So after getting the value of x, we can now find the value of R1. And therefore R1 will be 2.67 ohms. After getting R1, since R1 plus R2 is equal to X, then we get R2, not R1. This last equation should be R2 equal to 4 minus 2.67 and giving 1.33 ohms. So that is the second example. This example is based on the principle that we studied in an earlier lesson. I think that was lesson 2, talking about determination of a known resistance as one of the applications of the potentiometer. Okay, example 3. In the circuit shown on the next slide, the EMF of the standard cell is 1.02 V, and this is balanced by the PD across a resistance of 2040 ohms in series with the potentiometer wire AB. So that is the diagram. AB is 1 meter long and has a resistance of 4 ohms. Calculate the length AC on it, which balances the EMF of 1.2 millivolts of the thermocouple. Now, we have two galvanometers in this diagram. One is connected in series with the standard cell, another one is connected in series with the thermocouple. They both show no deflection. In the first case, if this first galvanometer shows no deflection, it means that the PD across the 2040 ohm resistor is the same as the EMF of that cell ES. So since we don't know the current passing through that resistor, call it I, we can use that concept to find the value of that current. That is exactly what we do first. First get the current, and once you got the current and you also have now the resistance per centimeter of the wire as 4 out of 100, we can therefore get the PD per centimeter of the wire. Having got the PD per centimeter of the wire, and since we know the EMF of the thermocouple, then we can get the balance length. Substitute those values and get the balance length as 60 centimeters. So that is the end of the lesson. Thank you very much for listening to me. This is also the end of the chapter. God bless you.